Module 3, Dynamic Equilibrium and Differential Equations. The learning outcomes for this module are as follows. First of all, we're going to see what is equilibrium and what is the difference between static and dynamic equilibrium. We're going to use a differential equation in a real-life application, and we'll see the reason for solving a differential equation. We saw in the past modules that with arithmetics and algebra, we set the foundations for calculus. We saw that the iterative multiplication of a number by itself results in exponential growth. As for exponential growth, the most important function is e to the power of x. This is illustrated on the right-hand side of this slide, where e to the power of x, 3 to the power of x, and 2 to the power of x are shown. The reason for e to the power of x to be the most important function is because it's the only function whose rate of change is equal to itself, as illustrated in the differential equation. This, on the other hand, makes it useful to model growth that feeds on itself. The purpose of this active learning activity is for the learner to stop for a moment, look at the equations that are shown on the left-hand side for a spreadsheet implementation of the exponential function that we just described. If you do the programming of these steps on a spreadsheet, you will be able to replicate the animation that is shown at this point in time on the screen. You can see that the proximity of the two curves, one being the exponential and the other one being the rate of change of the exponential, approach each other as the sampling time gets smaller and smaller. As for equilibrium, equilibrium is a state of balance between opposing force or actions that is either static, as in a body acted on by forces whose resultant is zero, which can be illustrated by this Jenga pile, or dynamic, as in a reversible chemical reaction where the rates of reaction in both directions are equal, as can be seen on this Petri dish. Why is equilibrium important? We can see that static equilibrium means a static structure, such a building, not being stable will collapse. As for dynamic equilibrium, we can see the disastrous consequences of a rocket not being stable during launching. Clearly illustrated here, equilibrium is very important. The topic of equilibrium, or the topic of evolution of dynamical systems, is very wide, and I will try, however unsuccessfully this is likely to be, to shrink it into a nutshell. In an automatic control system, its agility is tied to high-performance controllers, which implies a narrower margin of stability. In avionics, the difference in maneuverability of a jet fighter and a jetliner is that the former is built inherently unstable to make it very agile. And as for complex systems, they evolve by steering away from equilibrium and instability until they go to the edge of chaos. Chaos, in this case with capital, is because we are referring to chaos theory. In other words, and as a wrap up for this attempt to explain a little bit of the importance of equilibrium, really in a dynamical system, the importance of the equilibrium is the ability of the system to come back to it as soon as it can. Differential equations, as stated by Boyce and Di Primo, are important because many of the principles or laws underlying the behavior of natural world are statements or relations involving rates at which things happen. When expressed in mathematical terms, the relations are equations and the rates are derivatives. An equation containing derivatives are differential equations. A differential equation is very useful in real life as they allow us to model the most relevant traits of a given dynamical system that we want to study. To solve a differential equation, a mathematical expression needs to be found, but this is not always possible, as we'll see in the last module. In any case, the solution of a differential equation allows running scenarios and forecasting of outcomes. Just keep in mind that, paraphrasing the Danish proverb, forecasting is very difficult, especially about the future. Differential equations can be used to represent dynamical systems. We are displaying here a ordinary first-order differential equation that can be used to model what happens with the level on this toy pilot plant when I remove the finger from the bottom of the bottle where a hole has been drilled. You can see that the water is coming out fairly quick, as at the beginning of the simulation is sped up many times, and at the end we can see how the flow becomes very, very slow. What would be the use of a simulation? Well, to begin with, we wouldn't even need the bottle. We can see here a similar behavior on a simulation, and the trend showing how the level goes down and down with time. The conditions for dynamic equilibrium are also possible to find by using the same differential equation, because dynamic equilibrium is reached when the rate of change is zero, as shown in this equation. In this video, we are going to illustrate how, the starting point being 6.5 centimeters, we are going to stop the water from coming out. The water will go up, and then we are going to release the water again, and you will be able to appreciate how at the end the level repositions itself at 6.5 centimeters. Let's see it. Here we block. We can see the water going up and up and up. It's going to go up to about 9.5 centimeters. We remove our finger from the bottom, and then we'll see speeding up the simulation. Not the simulation, speeding up this recording several times, and you can see how the level came back to 6.5 centimeters. As another active learning activity, the learner is invited here to look at this description of a simulation that can also be done for a dynamical system, in this case being the accumulation of money in the bank when the bank is giving us a 2% interest rate, and there is no withdrawal or any other addition of money throughout the entire simulation. You will be able to see, first of all, that the simulation can show you exponential growth to begin with, and the second thing that is going to be important to see from this simulation is that you don't need to do a simulation per se if you manage to have a solution to the differential equation. Like in this case, it shows a mathematical expression, a of t equals to a sub 0 times e to the power of rt. This is animated in this slide, and then you will be able to compare your simulation to what is being displayed here. And this concludes our third module.